Today we're going to talk about recursion, and recursion is basically a way of repeating code or doing code multiple times, but without using a for loop or a while loop. So it's a different way of repeating code. And it's used to solve a lot of interesting problems, so we're going to see a couple of those in this chapter. But basically recursion is talking about a method calling itself in a different way. So here I have a method called message, and message basically calls itself. So message has a print statement and it's going to call itself. Now, can anyone see a problem with this method? What would happen if I type this method up into NetBeans and click run? What will happen? What will get printed? So maybe pause the video and think for a while. Well, this method will give us an infinite loop because message will print recursive method and it will then call itself, which is going to come back, print recursive method and call itself, and it's going to keep doing that forever. So this will give us an infinite loop. So what if I want to write it without having an infinite loop? Well, if I want to write it without having an infinite loop, then I need to know how many times I want to call message. So if I told you I want you to print, recursive method, let's say 50 times, what you would do is you would come here and you would write some kind of for loop or while loop, right? So if I wanted to print 50 times, I can do it with a for loop. I can say for int I equals 0, I is less than 50, I plus plus, and then I'll do my system.out.println hi. So if I run this code, it will run and print hi 50 times. I could have also done it with a while loop, and both will have worked. Now, what about recursion? How would I do it with recursion? Well, if I want to do it with recursion, let's start up a method, static void message. What I want to do is I want to print hi. Okay? So this will print hi one time. And then I want to kind of call message again to print hi again. But we said if we do that, it's going to run into an infinite loop. And if I run it right now, it's going to hang my NetBeans, so I'm not going to demo it for you. You can try it on your own. So how can I make it stop? So there has to be some kind of test to make it stop. So in our for loop, this test in the middle is what's making us stop. So here, how would I make it stop? Well, I can make it stop if I know that I am done. So I need a counter variable. Just like here, I have a counter variable that's helping me count from 0 up to 50. I need a counter variable here also that helps me count. So this method can't just be a method that takes nothing. It really needs to take an I or a count variable. Okay? So if I have a counter variable that's telling me how many times I want to call it, like here, for example, I call message with 50. So here, message is going to get called with 50. I'm going to print hi, and then I want to call message again. Well, I already did it one time, so what's left? If I already did it one time, that means what's left to do it would be 49 times. So that means I want to call count with -1, right? So if this is 50, I'm going to do one of them, and now I'm going to say call message with 49. And then when 49 comes, it's going to print hi and it's going to call message with 48. And it's going to keep going through that and doing that many, many times. But when is it going to stop? I don't have any test. So right now I have a number that's going down, but I don't have a test that makes it stop. So I need to really add a test. When do I really want to stop? When do I want to stop? I want to stop when I don't have any more count, when count reaches 0. So maybe I can say if count equals 0, then do nothing. Or here I'll say if count does not equal to 0, so if it hasn't reached 0 yet, then I will print and I will call message. And so this will be my test to stop. So when we're doing recursion, yes, we might not be using a for loop, And yes, maybe we're not using a while loop, but we still have to have some starting point. We still have to have a test, and we still have to have an update. Those three things that we talked about with for loops and while loops still exist with recursion. So here, what's my starting point? Here I'm starting with 50. Now here I'm doing it backwards. So if I wanted to kind of modify this rule, this for loop to do the same thing, I would say for I equals 50, while I is greater than 0, I minus minus. So here I'm going backwards, 50, 49, 48, all the way until I reach 0. When I reach 0, I'm not going to print anything. So the same way here, I'm starting off with 50. That's my initialization. I'm saying I want you to do it 50 times. My stopping is when I reach 0. So as long as it's not 0, I'm going to continue. So I can also say while count is greater than 0. Okay, so it matches the for loop. Both will work. This will work, and if count does not equal 0, it will also work. And then when I'm done doing this, I want to update my count to be -1. I want to say I'm going to do it one time less, so I'm going to call message with count -1. So this will achieve the same result as this for loop. Now I'm going to comment out the for loop, and I'm going to call message with a smaller number, 5, so we can actually see and count them ourselves. And so message here got called with 5, and then it made it 4. It's calling message with 4, and it's printing that. Then it's calling message with 3, message with 2, message with 1, and then when message got called with 0, it said it's not greater than 0, so it didn't do anything and it stopped. So this is the basic idea of recursion. Again, you still have to have like an initialization. You're starting with some value. You're going to test and make sure that value reaches some stopping point. And then you also have to make sure you update your variable. But basically, the definition of recursion is a method calling itself again. But it's calling itself with a smaller task. Here, message was called with 50 initially, or 5. And then it's calling itself with a smaller version. Now I want you to do it with only 4. And 4 is calling itself again with 3, and so on. And so here, what we did to fix that infinite loop was we added a test. And this is the test that makes the loop end and not become an infinite loop. Now let's do more practice. So here, what we want to do is we want to write a method that takes 2 integers and prints the numbers from the first integer to the last integer. And I'm going to do it in the video, but I would highly suggest that you kind of pause the video and try doing it yourself. So let's do it first with a for loop. So with a for loop, actually let's write it here as a separate method. Public static void, and I'm going to call it print range because it's printing the range of a number. Let's call it start and end. And if I wanted to do it with a for loop, what I can say is for int I equals 0, I equals start. So I'm going to start with start. I'm going to go until I reaches end. Here I want to include end, so I'm going to put an equal sign, and I say I++. And then I'll say system.out.println I. So if I go up to main and I say I want you to call print range 10 to 20, what it's going to do, it's going to come start off our I with 10, and it's going to keep printing 10, 11, 12, 13 until it reaches 20. It's going to print 20, the end, and then when I becomes 21, it's not going to print it. So this should print us the numbers from 10 to 20, and it does. Now, how about if I want to do it with recursion? So let's create a function, a method, call it print range recur, and it needs to take a starting and an ending. And what we want to do is we want to break this problem into 2 small things. We want to do something one time, kind of like here the message. what we did was we said we're going to break this problem into two smaller parts. One part is just printing high one time, and then the other is saying, okay, now I did it one time, now go do this thing that was 5, do it one less, 4. So now if I want to print the numbers, let's kind of think together. If I want to print the numbers from 10 to 20, what I can say is this is the same as printing 10 and then adding to it printing 11 to 20. And printing 11 to 20 is the same as printing 11 and then saying I'm done with 11, so I want you to print me from 12 to 20 and so on. So what we're doing is we're breaking up that range that was printing 10 numbers. Now we said we're going to do it one time for you, and now you only have to do 9 numbers. And the 9 numbers, we do one of them, and then we say we have to do it now 8 times, and so on. Now, when will I stop? Just like here, we said we're going to stop when we reach the number end. Here, we could also say the same thing. So if I ask you to print 20 to 20, for example, you're going to say, well, that means I only need to 20, and that's it. I'm going to stop. That's it. That's the end of my recursion. So whenever you're thinking of how to do recursion, you're asking yourself, what is it that I need to do just one time? What's a simple task that I need to do one time, like printing the number 10? And then how do I break this big problem into a smaller version of it? Instead of printing 10 numbers, now I've just made it be 9 numbers. And the 9 numbers, I made it 8 numbers. And then you ask yourself, when are you going to stop? Well, here I'm going to stop when start and end are the same. So we can start with our stopping. If start equal end, if they're the same, then I don't have to do anything, right? So instead I can say, well, why if start does not equal end? They're not, I haven't reached my end. What am I going to do? Well, the first thing I'm going to do is print the starting number. Okay. And now I'm done printing the starting number. So now I'm going to call myself again and say, I want you to print from my next number, start plus 1, all the way to end. So you're doing one part of the problem by printing just one number. And then you say, okay, now I'm going to call myself again with a smaller version. Now I want you to print me start plus 1 until the end. And I know that I will eventually stop because I know that start will eventually reach end. So let's try that. Print range rec. So instead of calling this one, the normal one with the for loop, we're going to call print range rec, and we're going to give it 10 to 20. And let's see if it does the right thing and print the numbers from 10 to 20. Ooh, and it didn't. It printed 10 to 19. So let's go and try to fix it. Why did it do that? So here, when start is not equal to end, okay, so if it doesn't equal to end, so when I called it with 20 and 20, I really want it to print 20, but it doesn't here because I said they're not equal print. So here I might want to say else system.print ln start. So if I reach the end, I just want to print it one time, but I don't want to call the recursive method. So I don't want to call the recursion here. Let's try that one more time. And now it prints the 10 to 20. Okay, so this is how we do recursion. Now, solving problems with recursion involves the same basic idea of for loops and while loops. You have to say your starting point, your stopping point, and your update. Now, instead of calling the stopping point, the I less than or equal to something, that stopping point, we call it a base case. So we say, you know, what if you get a 0? What if you give an account of 0 to print? What are you going to do? Well, I'm not going to do anything. What if you're given a number start and end that are the same? Well, I'm only going to print the number that is given that's the same, like the 10 or the 20 that we were just given. So a base case basically is just, if you just want to do this one time, or if you get a 0, what are you going to do? This is called the base case. And the base case, if you have the base case, then you know exactly what you're going to do, and you're just going to do one step. Now, if the base case cannot be solved, if the base case is not true, star does not equal end, count is not 0, then what we do is we reduce the problem into a smaller problem that is kind of the same. So what we're doing is we're reducing the problem to do something less. And every time we reduce the problem with the recursive calls, we're going to eventually reach that base case. So if I'm called with message of 10, I know that eventually I will be called with message of 0, which is not going to print anything, and that will stop. Now, another problem that we can do that's famous with recursion is called factorial. So the factorial of a number, it's a non-negative number, you do like n factorial is n like exclamation mark. And basically what this means, if you have a number and you want to know the factorial of it, what you do is you multiply all the numbers from 1 up to that number. So if I tell you 5 factorial, what's the definition of 5 factorial? You will say it's 1 times 2 times 3 times 4 times 5. If I tell you 100 factorial, it's 1 times 2 times 3 times all the way up to 99 times 100. Well, what is the base case for factorial? They tell you that if n is 0, okay, 0 exclamation mark, 0 factorial is actually 1. And then anything after that, you know. So if I tell you 0 factorial, you know it's 1. If I tell you 1 factorial, well, that's 1 times nothing, so it's also 1 factorial. If I tell you 2 factorial, then you know it's 1 times 2, and so on. So 0 is just 1, the factorial of it. So we want to write this using recursion. So let's think of how to do it using recursion. Public static void factorial. And factorial is going to take a number. So they told us the base case. They told us if n is equal to 0, then you know that you're going to return just 1. Yeah, so here it can't be a void method. It has to be a value returning method. So if I ask you, what's the factorial of 0? You're going to tell me. Well, what if I ask you the factorial of any other number in the world? Well, you know that the factorial of any other number in the world is going to be that number times the factorial of 1 minus that number. So here we're doing it backwards. In the slides, it's telling you that n factorial is 1 times 2 times 3 times all the way up to n. Okay, so that's what the slides are doing. Here, what we're doing to implement it is slightly different. We're saying that n factorial is n times n minus 1 times n minus 2, n minus 1 times n minus 2, and we're going to go all the way until 1. So we're just doing it backwards, okay, so that we eventually reach that 0 that we have here. So if you tell me what's 5 factorial, for example, I'm going to tell you that 5 factorial is 5 times the factorial of 4, and that is 5 times 4 times the factorial of 3, because factorial of 4 is going to say I'm 4 times the factorial of 1 less than me, and factorial of 3 is going to say that I am 3 times the factorial of 2. And let's just continue this so you kind of see what it's doing. And then if I just copy the 5 times 4 times 3 from before, and then go to the factorial of 2 and say, what are you? It's going to say, oh, I am 2 times the factorial of 1. And then if we just copy again the first part here, and we go to factorial of 1, it's going to say I'm 1 times the factorial of 0. And here we've reached the base case, because factorial of 0 is just 1. So this will be 5 times 4 times 3 times 2 times 1 times 1. Okay. So here we wrote factorial in a recursive way. Let's now call it with 5 and see if we got the right answer. So if I say system.out.println factorial of 5, and let's kind of do it together so to see what 5 times 4 is. So 5 times 4 times 3 times 2 times 1. Oops. So 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So if we did it right, we should get 120. And let's test it out. And we do get 120. Okay, so this is how we would write factorial in a recursive way. So the key here to show you is that you always need to say, if I want to do factorial of some number, how will I break this up into a smaller problem? So here I am saying that it's going to be just n times factorial of n minus 1. And this is the breaking down the problem to something smaller. Factorial of n, we're saying what it is. If I do factorial of n minus 1, what do I need to do to this to actually get factorial of n? So if I have factorial of n minus 1, I need to multiply it by n. And then you ask yourself, what is the base case? When will I stop? So here we're saying we're going to stop when we reach n is 0. We could have also said we're going to stop when we reach n of 1. So if n equal 1 would have also been a valid base case. But because the slides told us to use 0, that is what we're doing. And so here, this is the code that is very similar to the one we wrote in the slides. Now, talking about recursion, recursion is a powerful tool. It is really nice in solving repetitive problems. But I just want to tell you that it's not always necessary to use recursion. You won't find a piece of code that you must use recursion to solve. Anything that we're doing with recursion, we could have done it with a for loop or a while loop. However, there are some problems that are easier with recursion, and we'll see examples of that. So just to reiterate, recursion is never absolutely required. Okay, you can get by with for loops and while loops and if statements. Anything that you could have done with recursion, you could have actually done it with any kind of other loop, like a for loop or a while loop. Now, is recursion nice? Yes, recursion is nice, and we'll see examples in the next slide. However, we just want to say that there are some problems with recursion. And recursion, when we're doing things repetitively, we are allocating a lot of memory and saving it in RAM, and we're not letting go of that RAM space until the method ends. What does that mean? So let's come here to, let's come here. So here, what I did with this factorial, or let's look at message, for example. Let me open up Paint so I can kind of show you what's happening. So we have message, okay, and it got called with a count variable, and that count variable was 5, okay? And then what it did was it checked if count was greater than 0. It is. So it's going to print hi, and then it's going to call message again with count minus 1. So now message is going to call itself, and this time it's going to call itself with count 4. So now we have a variable in RAM that has a value of 5 and a value in RAM that has 4. Okay, because this variable count is not going to go away. It's not going to go away until the method ends. So this count got created here, the variable. It's not going to go away and get cleaned up by the garbage collector until this brace closes. And it hasn't, because we're still here. We're calling count. We're calling message with 4. Message with 4 is going to call message of 3. So now I have count with 3. And that's going to call message with count equal 2. And that's going to call message with count equal 1. And that's going to call message with count equal 0. Now, when 0 hits, it's going to say, oh, well, 0 is not equal to greater than 0. So it's going to finish and start, doing nothing. And it's going to start returning back and finishing. But when this message of 5 is getting called, we have 1, 2, 3, 4, 5, 6. We have 6 spots in RAM allocated. We have 6 ints in RAM. Okay. Now, compare that to the non-recursive version of it, the for loop that we wrote here. How many ints do we have allocated? We only have one int. Only one int. So here you have 6 ints allocated in RAM versus 1 int when I used a for loop. Only 1 int. So which one is cheaper? The for loop is cheaper. It uses less RAM. Okay, so that is one thing. You have all these variables that you're holding on to because RAM is not going to let go of these variables until they go out of scope. They go out of scope when the brace closes. And because these are nested instead of themselves, they're not going out of scope. So okay. Another thing that you are doing is that the compiler, not the compiler, sorry, the JVM, the Java Virtual Machine, needs to remember these calls. So when message calls message again, and then, you know, this one calls this one and this one calls, and they keep calling each other. When this message return finishes, it needs to return back to message of 1 at that same line. So when message of 0 is done, it needs to come back to this message. Let's do something. Let's throw an exception here. I'm just gonna throw an exception. If count equal 1, let's do this. Just gonna force an exception to be thrown so you kind of see what's happening. String name equal to test, and let's do a system.out.println name.char at 100. And there is no char at 100, of course, because it doesn't contain that. So let's run and see what happens. Oops, we need to call message. Let's go up here and call message. Okay, so an exception happened. And here you see the stack trace. So main called message of 5. Message of 5 called message of with 4. Message of 4 called 3, called 2, called 1. So here, do you see how message is calling itself many, many times? This is called the stack trace. It's very deep. Message is calling itself many, many times. Every time a method calls another method, whether it's itself or another method, it needs to remember, you know, where it called it from, like at line 36. Because if anything happens, it needs to report all that, right? So it needs to remember where it called it from. So this stack trace, okay, is expensive. It takes up some overhead from the Java virtual machine to remember every method, what it called at what line and what file. So this is an extra overhead that we can avoid if we don't use recursion. So recursion is nice, but there is overhead that is associated with it. Those extra variables that we're allocating in RAM and we don't let go of, and that stack trace that we have to remember. The JVM has to remember who called who at what line in the file. So why is it that we use recursion if there are problems? Well, because sometimes things are faster and sometimes they're simpler to execute. So if we look at a famous example called the Fibonacci series, and the basic idea of it is that you have a base case. Fibonacci of 0 is 0, Fibonacci of 1 is 1, and then the Fibonacci of any number is the Fibonacci of the number -1 plus -2. What does that mean? So here we have Fibonacci of 0 is 0, Fibonacci of 1 is 1, and so if you go and you want to find 2, you're going to say, well, it's going to be the last 2 numbers before me. It's going to be 1 plus 1. And 3 is going to, like, the next one is 3 plus 2. And the next one is 2 plus 3, which is the 5. And then the next one is 5 plus 3, so 8. And then the next one is 5 plus 8, 13, and so on. Now, if you want to implement this with recursion, it's very simple. You just put your base cases. If n is 0, return 0. If n is 1, return 1. Otherwise, return the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Now, I want to challenge you and see how you can implement it without recursion. And you're going to be going in circles and trying to find a way to do it. It's not easy. So because of simplicity, we would use recursion to define this method. Now, Is this expensive? Yes, because if I want to compute Fibonacci of 6, it says go and compute Fibonacci of 5 and 4. And to do 5, I have to compute 4 and 3. To do 4, I have to compute 3 and 2. To do 3, I have to compute 2 and 1. And if you look at this, each one what they're doing, now I had to compute like Fibonacci of 3, for example. I had to do it 1, 2, 3. I'm doing the calculation over and over and over, the same calculation. Here I had to do Fibonacci of 4 twice. Fibonacci of 2, I had to compute it 1, 2, 3, 4, 5 times. Is that expensive? Yes. Am I doing extra work computing the same thing over and over and over? Yes. But why am I choosing recursion? Because of simplicity and implementation. So yes, using recursion sometimes is slower, sometimes has extra overhead, but it's simpler. And like I said, I do challenge you to try to implement the Fibonacci series algorithm without recursion and see how complex it's going to be. It's not going to be 5, 6 lines like this. It's going to be a little bit harder. Okay. Another famous example is the Towers of Hanoi, where you have these pegs and you are challenged to move them all to another peg. But when you're doing the moving, you cannot stack a big peg on top of a small peg. So you have this extra peg in the middle that helps you. And here there's a video. I would urge you to pause the video, my lecture video, and look at this video to try to see like how it's doing. It's going to solve it for you and show you how to do it. So it's an interesting game, and this is the algorithm for it. We're not going to go over it. But if you were to implement it in recursion, it's only a few lines of code. Not very complicated. Once you understand the algorithm and someone tells you how to do it and the idea behind it, implementing it in code is not hard. Now, if you were to do it without recursion, it would be really, really hard. So this is why we do recursion. We use recursion to solve sometimes hard problems and complicated problems using simple algorithms, even though we have some overhead. Another practice is like, let's say you have permutations. If I tell you, for example, the word eat, what are all the different ways that you can rearrange these letters to come up with all different versions, like all different words or combination of letters from the word eat? Well, you can do E, you can have E, A-T, or E-T-A. And then maybe you can take the letter A and say, well, I have A, and then E-T or A followed by T-E. And then you can go to the letter T and say, well, I want T followed by E-A or T followed by A-E. So when you come and look at it, basically what you're doing so when we want to look at all the ways of doing different words or letter combinations of eat, well, I'm taking the first letter, the E, and then I'm saying, okay, what are all the different permutations that I can do with A and T? And then I'm going to take A and think of all the permutations that I'm going to do with the letters E and T. And then I'm going to take the last letter, T, and think of all the permutations that I'm going to do with the other two letters, A and T. Now, when I go and look at the permutations of A and T, well, that is just A plus all the permutations that I can do with the letter T. And this is E plus the different permutations that I can do with the letter T. And this is A plus all the permutations I can do, again, with the letter, this is E. Okay, so now if I tell you what's the permutation of T, well, there's only one way of doing T, which is just the T, right? And so here, what you're doing is you're trying to break up the problem into a smaller version. So the permutation of eat is now E plus the permutation of only 2 letters. And now this part is the permutation is A plus the permutation of that. So you're breaking it up into smaller pieces. Okay, so here it's E plus. And so you can write this algorithm also in recursion. We're not going to write it together, but I wrote it here. And let's just look at it together. So here I'm taking a permutations, I'm taking a string, a word, and I want to find all the different permutations. So I'm going to return the result as an array list of strings. So if you only have a word that has only one character, just one letter, that's easy. That's our base case. So I just have a word that only has that one letter. Well, what if I have more than one letter in there? What I need to do is go through every single character, the first character, every character, and I'm going to take that character out. So I'm taking like the E out, for example, and then I'm saying, okay, now what I want to do is I want to do a permutation of all the other letters in this word. So when I take the E out, here what they're doing is I'm looking at character at location I. So I'm going to take a substring from 0 to I, and then from I plus 1. So I'm skipping I because substring 0 to I doesn't give me letter I. And when I'm doing my permutations, I'm going to take that letter I, the letter at location I, and add to it all the strings that I got from the permutation. So I'm taking all the letters from the word except the letter at location I, because this will not give me location I. And I'm saying, okay, give me all the permutations with these letters. So here, take all the rest of the letters except the letter that I'm looking at right now, get me all its permutations. Now you give me all those words. I'm going to go through all these words and append them to I. So if the word was eat, I would have E plus all the permutations that came from the A and the T, which would be at and ta. And so here is an example where you can use recursion to do something like a permutation. There's a lot of use cases for recursion, and basically what I want you to know is how to do a simple things with recursion. So here what I want you to do for this classwork is think about multiplying in terms of addition. So if I tell you I want you to multiply 4 by 7, well, 4 by 7 is basically taking that 7 and adding it 4 times. So how can you write this in recursion? How can you break up 4 times 7 to be adding 7 4 times? Is it the same as maybe adding 7 plus the product of something 3 times and then 2 times and then 1 time? So think of how you can simplify multiplication and do it in a recursive way using the concept that multiplication is just a bunch of additions, and then try to do that. You'll find that it's like 2-3 lines of code. Once you do it, you can test it on HackRank to make sure you got the multiplication correct. But really, you're going to find that it's simpler. So always ask yourself when you're thinking of recursion, how can I break up a problem into a smaller problem? So if I'm asked 4 times 7, how can I break that into something smaller, like, for example, 3 times 7? And then what is the base case? When do I know the answer immediately and I don't have to do any calculation? For example, like 1 times 7.